Today's little math and physics chat is on conservation. And I'm not talking about conservation like Smokey Bear, Save the Forests, protect the environment. That stuff is really important too. But I'm talking about conservation as in conservation of mass, conservation of energy, the physics conservation. And in physics, conservation is a law. Nothing is created, nothing is destroyed. So in particular right now, I'm going to focus on conservation of mass. And that's because in geomorphology, we are concerned with how mass is moved across the surface. And moving masses, whether it's eroding or depositing, is what shapes our topography. And, if these objects could be squished or stretched, then there actually might be a complicated relationship between moving masses and changing topography, right? Because you might be able to have something that's really, really huge, and then squish it down into the size of a tiny speck, and then move that to another place on the Earth's surface. So I have my little landscape and, fuzzy tree. And then that thing creates just a tiny little dot as opposed to creating some massive hill. So here's the question then. How do we think about this and how do we try to simplify this problem? It turns out that most things on the Earth's surface, things like rock that we think about, are not actually going to change their volume very much at all. So in fact, we can create this simplifying assumption that we are just trying to conserve volume. All right, so from this, then let's think about it. So I'm going to say that there's a big basket right here, or a big hole, and we have two stick figures. The one on the left is holding a big shovel. Let's see if I can do this. Oh, that's a terrible shovel. Let's try this. I think it needs a flat, and there we are. That's a lot better. So big flat shovel, and it has a whole pile of rocks. And as our little character at the left is moving her rocks into this bin starts to fill up. And so first it has this layer down here, and then a few more show up on top of it. It's probably clear, but rocks are not going to actually overlap and merge together like this. This is just my sketching ability that we're fighting against. And the rocks are going to fall all the way down until they're touching each other. And so the more rocks that this character at the left throws into this bin, the higher this pile is going to get. Now I have a second stick figure over here on the right, and this stick figure has a long stick figure of the stick, that has a little grabber arm, so you can think about like, a claw game or something, and is pulling these out as fast as possible and throwing them somewhere else. It doesn't matter where they're throwing them. Let's just say they're throwing them into their car, breaking the windows, and creating all sorts of chaos. But they're pulling it out. And for whatever reason, this person who's pulling it out is so good at it that they aren't necessarily going to be slower than the person shoveling it in, which is kind of what would be obvious. And what we want to know then is, how is the height of the rock pile going to change over time? So delta is what we use for change in height of rock pile over change in time. Well, if we say that this box has some sort of width, and I realize I shouldn't have drawn that height there, but too late now, I'm just going to call that width B because that's the British breadth. And that's what we end up using for rivers as well. And we're trying to figure out the height of this rock pile changing over time. Well, what we can say is that the change in the height over the change in time is going to be equal to the amount of stuff going in minus the amount of stuff going out divided by the width, which is this B. And so what that means is that the change in the height of the pile, I'll mark that up here too, The change in the height of the pile is going to increase if there's more in than out, and it's going to decrease if this little claw person is winning and pulling more stuff out than the shovel person can put in. And that it's amplified or dampened by this term B. So if it's a very, very wide area, it's going to take a lot of shoveling or grabbing to change anything in terms of the thickness of this pile. But if it's a really narrow box, then it's actually going to be pretty easy for them to, shovel one rock in and change the height by a lot, or pull one rock out and change the height by a lot. And so this is conservation, and this is the way that we're going to approach it when we start to build differential equations to describe landscape evolution.